Hi, and welcome back to Codex. Today we have Sam Ballas from Florida State. Professor Ballas is an expert in manifold theory. Today he will tell us about frame theory for vector bundles. Please take it away, Sam.
Thank you very much for the invitation to speak here today. So as you mentioned, my background is kind of in geometry and topology. And a few months ago, if you had asked me what my prospects of being invited to speak in a seminar about like theory and applications of harmonic analysis, I would have put that as pretty low. But alas, here we are. And I'm very excited to be here talking to you today. So this is about some work that I've been doing recently with Tom Needham here at Florida State and Clay Shonkwiler at Colorado State. And in some sense, it's going to be a play in three parts. So to start with, I'm going to sort of talk about frames. And I suspect, given the background of the people here, a lot of you will know some of this stuff. But I'm hoping that maybe the way I think about frames is a teeny bit different than the way you think about frames, just because of my background, and that maybe I can give you a little bit of a slightly different perspective on these things and how I think about them. And in particular, I think the way that I think about them is sort of amenable to what will happen in the second and third parts, where we talk about, well, what are vector bundles and like why might you care about them, and what are sort of frame fields on vector bundles. So again, if you have any questions, please feel free to stop me as we go along. But all right, let's get going. Okay, so let's sort of imagine that we're in a real Hilbert space. And so, like I said, I'm a geometer, and so the sort of cardinal sin you can commit as a geometer is sort of picking coordinates. And so I want to pretty much do everything without picking a basis for this Hilbert space. And so I want to introduce these objects called frames that I suspect many of you are familiar with. So what a frame is it's a collection of vectors in my vector space indexed by the natural numbers, so that I have these constants A and B, so that the sum of inner products with the vectors satisfies some inequalities depending on lengths. So the sort of upper and lower bounds I would regard as quite geometric because they're talking about the lengths of vectors in my Hilbert space. But the middle term is maybe a little less geometric, but we'll sort of come back to that. And so this thing is typically called the frame inequality. So for my purposes, I'm going to care mostly about finite frames. And for me, what a finite frame means is that basically, except for finitely many things in my collection, all of them are zero. So you can sort of think about it as a finite subset. But anyway. Let's sort of think about this a little bit. So if you have a finite frame and you pick a vector that's in the perp of the span, then your frame inequality, the lower one, is telling you that the length of that vector had to have been zero. And so if you kind of unpack what that means that the span of your vectors has to be dense in your Hilbert space. And so a couple of quick observations. Well, if I have a Hilbert space with a finite dense subset, that ought to mean that it's going to be finite dimensional. All subspaces of finite dimensional vector spaces are closed, and so that tells me that a finite frame is in particular a spanning set for my vector space. All right. So from now on, I'm going to assume that my vector space is finite dimensional, and that I have a finite collection of vectors in it that maybe is or is not a frame. We'll come back to that. Okay. So if I have a finite subset of vectors in a Hilbert space, then this gives rise to a so-called analysis operator, which is going to be a linear map from my vector space to the space Rk, whose dimension is the same as the number of vectors I have. And what I'm going to do is for each vector, I'm going to interrogate that vector by taking its inner product with all the vectors in my collection. And then I'm going to use those as the coefficients of a linear combination in Rk. So that's what this analysis operator is doing. And if you sort of think back to the frame the frame inequality a little bit, this sort of sum that didn't seem very geometric when I first introduced it actually becomes a little bit more geometric once you introduce the analysis operator, because what this really is it's the length squared of the image of the vector v under the analysis operator if you use the sort of standard inner product on RK. And since I'm in a finite dimensional vector space, this is upper bounded by the operator norm of the analysis operator times the length of that vector squared, and that's in particular finite. And so what this is telling me is that the upper frame inequality is sort of gratuitous when I'm working with finite frames. It's sort of free, so I don't need to worry about it. Another thing I get in this context is a so-called synthesis operator. So this is a linear map that's going in the opposite direction. And so what it's doing is if you take a list of k numbers, well, I have a collection of k vectors in my vector space. So the most obvious thing to do is to just take that linear combination of the vectors. And so that's what the synthesis operator is doing. And if you think a little bit about it, you'll sort of realize that the synthesis and analysis operators are transposes of one another. This is an easy computation. And that actually gives me some useful information. So if the collection I started with was a spanning set, then that definitely means that my synthesis operator is surjective, because the image is just all the linear combinations I can build out of my collection of vectors. And then that means that by the sort of transpose property, the kernel of the analysis operator is orthogonal to the image of the synthesis operator. And so that has to be trivial. And so that means my analysis operator was injective. And that actually is telling me how I can find my sort of the constant for my lower frame bound. Right, so if I take A to be the infimum over the unit sphere in my vector space of the length squared of all of the analysis vectors, that's going to be a positive number because I'm taking an infimum of a positive thing over a compact set. And so I can use that as my lower bound. And so what's the sort of moral of all this is that finite frames in a Hilbert space are the same thing as spanning sets of that vector space. And they're also the same thing as surjective linear maps from RK to V. And in fact, this sort of latter perspective is the one that I'm going to be taking. I'm going to sort of tend to think about frames as being surjective linear maps from RK into my vector space, where I'm sort of
Sam,
identifying. Yes.
for this highlighted part, is M the same thing as SC?
Yes. So you can sort of task if you have a surjective linear map, you can identify it as the synthesis operator of some. So you take like the image of the standard basis in RK, and that will give you a frame. That will give you a spanning set, and if you sort of take that collection, then the synthesis operator is M. Any other questions? Okay. So I have these two linear operators, one from V to RK and one from RK to V. And so the most obvious thing I could do is to compose them with one another to get an automorphism of the vector space V. And this is the so-called frame operator. So how does this work? So if I have a collection of blue vectors in my vector space, maybe there's sort of more of them than the dimension would suggest, then I can apply the analysis operator to get a list of numbers, right? I'm just sort of taking the inner product of a fixed vector with all of the vectors in my collection, and that gives me a point in RK. And then I can sort of turn around and take that collection of numbers and use it to build a linear combination of my frame vectors, and that'll bring me back into my my original Hilbert space. And in general, there's sort of no reason for the vector and the sort of frame operator applied to that vector to have anything to do with one another. But we'll sort of come back to that in a little bit. But the reason I am interested in this frame operator is because it's useful in the context of vector reconstruction. So let's say I have a frame and I have a vector in my vector space. Then what I can do is I can use the analysis operator to give me a list of numbers that I think of as encoding that vector. And so if I want to recover my original vector from the encoded vector, then I can do a pretty straightforward thing. So first, I could take the synthesis operator of W, which by construction is the frame operator applied to my original vector. And then I can just invert the frame operator to recover the vector that I started with. So in order to do vector recovery, you have to sort of take this composition of these two linear maps, the synthesis operator along with the inverse of the frame operator. And this map actually has a name. I didn't know this until very recently. That this is actually what goes by the name of the Moore-Penrose pseudo-inverse. And it's typically denoted with a dagger. And so this is sort of tied up in vector reconstruction. So I want to talk a little bit about the Moore-Penrose pseudo-inverse because it's actually quite easy to describe geometrically. So if you have a vector in Rk and you want to compute the Moore-Penrose pseudo-inverse of it, what you do is you orthogonally project that vector onto the image of A. So in this picture, the little purple guy is the image of some vector space over here. And so first I orthogonally project W onto the image. And on the image, the analysis operator is injective. And so it makes perfect sense to invert it. And so if I invert it on W prime, I get the vector that I started with back. And so this sort of immediately tells you that if you're restricting to the inverse, that the Moore-Penrose pseudo-inverse like actually is an inverse. So that this is sort of a very nice geometric way of seeing what the sort of vector reconstruction looks like in this context. Okay, so a type of frame that I'm going to focus on that's going to be quite nice are so-called parsable frames. So I sort of talked recently about sort of how you do vector reconstruction using the Moore-Penrose pseudo-inverse. And a really nice instance of this would be if the frame operator was actually the identity operator on my vector space. So as I said before, there's sort of no reason for V and the frame operator V to be related to one another. But you could imagine a situation where where that is the case. In which case, it's very simple to reconstruct my vector. If I have a vector and I want to reconstruct it, I just interrogate it against all the vectors in my frame. I get a list of numbers, and then I take that linear combination of my frame vectors, and that gives me back the vector I started with. And so frames of this type are what are called parsable frames, I guess because of Parsifal's identity. And in particular, you can think about this as a generalization of the notion of an orthonormal basis. Like, so if you sort of thought about how you would write a vector with respect to an orthonormal basis, it's sort of exactly a formula like the one you see up here. So I want to sort of cast parsable frames in a couple of alternate ways, one of which is quite geometric. So as I said, you can define a parsable frame as one whose frame operator is the identity map. And if you kind of unpack what that means in terms of the frame inequalities, you see that forces both of the constants in that inequality to be 1. And then in turn, that's giving you a geometric property. So in general, the analysis operator of a frame is an injective linear map from your vector space into Rk, but in general, it doesn't play nicely with the inner products. And so in the case of a parsable frame, what you see is that the analysis operator is actually an isometric embedding. So it's preserving inner products on your space. And this actually characterizes parsable frames. They're sort of exactly the ones whose analysis operators are isometric embeddings. And so again, this is kind of how I like to think about them because I view it as kind of a nice geometric way of doing things. Okay, so what's a typical application? So a typical application you might run into is trying to do vector reconstruction in the presence of some sort of noise. So let's say that I have a vector and I use the analysis operator to encode it into a list of numbers. And then I want to call you up and tell you what vector I'm thinking about. But we're talking on a bit of a noisy line. And so when I sort of tell you the the numbers that I use to encode it, they get corrupted a little bit by some noise that I'm going to call eta. Then when I start trying to do recovery, I'm going to be applying the Moore-Penrose pseudo-inverse to the corrupted vector. And then I'll get a new vector v prime that probably won't be the vector that I first thought of. And so a question we'd like to ask ourselves is like, how does the size of the error in reconstruction compare to the size of the error, or like compare to the size of the noise? And so this is not a super hard question to answer with a little bit of linear algebra. So let's sort of imagine if I was doing this using a basis. So I have a basis for my vector space V, and I'm going to consider some sort of white noise. And so what I mean by that is I'm going to think of the noise as being a vector that's uniformly drawn from a ball of some radius sort of centered at the vector W. So here's kind of a little picture of what I'm talking about. So I have my encoded vector, and then I have some like random noise that's drawn from this little ball around there. And that's going to give me my corrupted vector. And then when I apply the Moore-Penrose pseudo-inverse, I guess here the Moore-Penrose pseudo-inverse is actually the inverse of the analysis operator because I'm using a basis. I'm going to get some other vector. And I want to know, like, what's the size of this relative to the size of that? And something that can happen is if the analysis operator is poorly conditioned, like if it has a large condition number, then the relative size of my recovery error can be quite large compared to the relative error of my noise. And so this is a situation where an orthonormal basis is handy because it's not hard to check that an orthonormal basis is sort of maximally well conditioned. And so what does that mean? That means that the sort of worst case scenario size of my reconstruction error is going to be like the size of the noise, essentially. So I get a pretty good recovery if I use an orthonormal basis. Now let's see what happens if I do this with a frame. So now I have sort of too many, or like I have more vectors than I need. And so let's sort of think about what happens here. So when I do reconstruction, the sort of noise is going to be the same, right? It's sort of random. It's sort of randomly drawn from a disk centered at W, and I get this vector W prime. And when I go to recover, the first thing I do is I orthogonally project onto the image of the analysis operator, and then I invert. And so the cool thing about this is that the distance from W to the projection of W prime is at most the size of the noise. So it's actually possible that the sort of noise didn't really corrupt the vector at all. So for instance, if the noise were completely orthogonal to my vector W, then when I orthogonally project it, I would get W back on the nose and I'd get perfect reconstruction. So this is sort of like an instance of like why you might want to use frames because they sort of decrease the amount of noise you get. And again, if the frame that you're working with is parsable, then the sort of analysis operator is maximally well conditioned, and so the sort of error you get is going to be bounded by the distance between the W and the orthogonal projection now. So I know that like dimensionality tends to get kind of a bad rap, and I sort of hear people always talking about this curse of dimensionality. But in our case, it's actually a blessing of dimensionality. So imagine that we have a frame whose size is very large compared to the dimension of our vector space. So what I'm going to do is I'm going to look at the image of the analysis operator, and that's going to be a very small subspace sitting inside of R to the K. And so I can take the orthogonal complement of the image, and that's going to be a very large subspace, and I can sort of sum them together to get all of RK. And so if you think about what this means, is that if I pick a random vector of some fixed size centered at W, it's very likely that it's close to being contained in U, right? And the reason for this is if I pick a basis that's sort of adapted to this splitting, there are relatively few coordinates over here relative to over here. And the sort of expected size of all of the coordinates is essentially the same. And so that means that sort of most of the length of the vector is sort of in this direction. And that means that the vector is almost parallel to you. And so that means if I orthogonally project, it's very likely that I'm going to get something very close to where I started. And so the sort of moral of this story is that the sort of larger a frame I use, the more robust it's going to be towards like things like white noise. So this is maybe some motivation for why I might want to use these things. So I think now I'm about to get to the part where I talk about vector bundles. So maybe this would be a good point to stop and ask if there are any questions. Okay. So I want to sort of take everything that I've been talking about and sort of migrate it to the setting of vector bundles. So loosely speaking, a vector bundle of rank K is a collection of vector spaces of some fixed dimension that are in some nice way being parameterized by some topological space M. And in the back of my mind, M is going to be a manifold, but it could really be whatever your favorite topological space is. So if I want to be a little bit more precise, I could say, well, I'm going to form a space E by taking the disjoint union of all of these vector spaces. And this sort of naturally gives rise to a projection map, right? So if I take a vector in E, it lives in one of these subspaces, and I can associate to that the sort of point that was parameterizing that vector space. And so in this context, I have that the preimage of a point in M under this map I've just defined is the vector space corresponding to that point. And I'm going to call such a thing a fiber. And then the notion of being nicely parameterized means that for every point downstairs, there's going to be a little neighborhood so that if I look at the preimage of that neighborhood under the projection map, it's as sort of simple as possible. It looks like the neighborhood I started with crossed with the fiber at P. So here's sort of a little cartoon of what's happening. So you can think about like an infinitely long cylinder as a rank 1 vector bundle over a circle. And what's sort of happening is the projection map is projecting the sort of horizontal lines down to points. And globally, this is not a product. Well, I guess never mind. Globally, it is a product. But what's happening is that on small scales, you can take little neighborhoods, and if you sort of think about what they correspond to in the bundle, you get this little like green product neighborhood here. And so this is sort of what the prototype of a vector bundle is. So this nice parameterization is that it's locally a product, although it may globally be more complicated. Okay, so one object that you get when you start talking about vector bundles are so-called vector fields. So loosely speaking, a vector field is a continuous choice of a vector in each fiber. If you want to make that a little bit more precise, you could say, well, a vector field is a continuous function, sigma, from the downstairs space M to the vector bundle, so that if you compose it with the projection map, you get the identity. So this is just a fancy way of saying that the vector that the vector sigma associates to a point P has to live in the fiber sitting over top of that point. And so kind of a little toy example that's maybe nice to think about is you could think about the base space M as being S2, which I'll kind of think about as being, say, the surface of the Earth. And then if I could think about the vector spaces as being the various tangent vectors to the sphere at a particular point P. So each of those is going to be like a little copy of R2. And then my vector bundle, if I sort of take the union of all of those spaces, that's going to be the so-called tangent bundle to the 2 sphere. And then an example of a vector field in this context would be like wind velocity at a given instant, right? So at each point on the surface of the Earth, you can measure the wind velocity, and that will give you a little vector that's tangent to that point on the Earth there. So that's sort of like a kind of physical instance of a vector field. So this is sort of the thing to keep in mind. Okay. So there's sort of like a nice physical interpretation of vector bundles. So one way you can think about a vector bundle is you can sort of think about it as like a laboratory, and it's a laboratory where the things you can measure are vector fields. So let me try to make this a little bit more precise. So let's assume that our bundle, our vector bundle comes equipped with a continuously varying inner product. So my vector bundle is built out of a bunch of vector spaces. And so I'm assuming that each of those vector spaces comes equipped with an inner product. And that if I move a little bit in the vector bundle to a different vector space, that the inner product doesn't change very much. So that's the sort of setting I'm in. And so I can think about a vector field in this context as some sort of a measuring device. And so how does a vector field measure another vector field? Well, it does so by sort of taking inner products. So if I have another vector field on my manifold or on my vector bundle, I can form a function from the sort of downstairs space to the real numbers, where what I do is I interrogate the vectors in my vector field against my measuring device mu. And so at each point, I get a number that's giving me like the value of a measurement at that point. So if you kind of think back to the sort of wind velocity example, you could sort of imagine that my measuring device is something that, so at each point, I'll say I'm gonna like look east along a line of latitude, and I'm going to set up a little device that measures the easterly like blowing of the wind at that point. And such a thing would be a vector field that I can think of as a measuring device. And that measuring device will be able to measure the wind speed at every point. It'll give me a number that's saying, okay, this is the sort of eastward component of wind at this point. I mean, I guess you have to be a little bit worried about, well, what do I do at like the North and South Pole where east doesn't really make sense, but let's not focus on that quite so much. That's actually, I mean, it's an interesting question, but maybe we won't think about it too much. But this is sort of the sense in which I can think about vector fields as measuring devices on my vector bundle. And so here's kind of a natural question that's maybe motivated by things we were talking about before. So let's say you had a handful of measuring devices. So again, these are a bunch of different vector fields. And somebody handed you another vector field sigma. Well, you could measure that vector field with each of your measuring devices. And the question you'd want to ask is, well, could I figure out what the vector field was just by knowing the measurements? And if you kind of think about this, what's sort of happening is that these measuring devices are like a bunch of different analysis operators at every single point on your manifold. So at every point on your manifold, you have k measuring devices, and you can get k numbers associated to your manifold or to your vector field. And so the answer to this question is sort of yes, if and only if at each point the vectors coming from your measuring devices comprise a frame in the vector space at that point. So this sort of motivates the following definition of a frame field on a manifold. So if I have a vector bundle and I have a finite collection of vector fields on that vector bundle, then I'm going to say that that's a frame field of size k if at every point on the downstairs space, the collection of vectors I get coming from the vector field is a frame for the vector space at that point. So here are some kind of natural questions once you have a definition like this. So the first question is, if someone hands you a vector bundle, will you always be able to find a frame of some size k? So I'm not going to fix what I want the size to be right now. I'm going to allow that to vary. Well, if the answer to that question was yes, then the next question you'd probably ask was, how big does k have to be, like, relative to the like size of the vector bundle, in order to find a frame? And then if you started to realize to know that you could find frames, you might want to ask yourself questions like, well, maybe could I pick these frames so that they're kind of everywhere nice? Like, could I pick them so that the frames were always parsable frames at each point? And so these are some questions that I'm going to try to answer in the, I don't know, remaining 10 or 15 minutes of the talk. So any questions before I move on? Okay, so let's return to our little toy example. So we have the tangent bundle of S2. So this is all the tangent spaces tangent to a two-sphere. And so a question you could ask yourself is it possible to find a frame field of size 2? So what would that mean? That would mean at each point I have to find two vectors that span the two-dimensional vector space at that point. Or in other words, I have to be able to find a global basis for my vector bundle. Well, it turns out that the answer to this question is no. You can't find a frame of size 2. And this goes back to a theorem of Poincare in the 1880s that sort of colloquially goes by the name of the Hairy Ball theorem. It says that if you have a vector field on a two-sphere, then you can always find some point on the two-sphere where the vector that vector field assigns to that point is the 0 vector. And so in particular, if we had a frame of size 2, it would consist of two vector fields. And in order to be a frame, you couldn't have either of those vector fields vanish at any point on the manifold, or else they'd have no hope of spanning the tangent space at that point. So this is sort of an interesting situation. So this is like very different than what's happening for vector spaces. Like every vector space has a basis, and the basis of the size of that vector space. But the sort of corresponding statement for vector bundles is very false, even for very simple examples. And in fact, it's not so hard to convince yourself that if you have a rank n or rank k vector bundle, then it's going to admit a frame field of size k if and only if the vector bundle is dumb. Like if it's like a trivial bundle, it's a product of the downstairs space and a vector space of rank k. So only very simple-minded vector bundles will admit like global bases. And yeah, so that's sort of the content here. You usually can't find a global basis for a vector bundle. And so like frames become all the more important. They're not just like some luxury that maybe allows you to do more effective reconstruction. They're actually something that you like might need to try to use if you want to have any hope of globally defining things. Okay, so now let's sort of ask ourselves, well, what about a frame field of size 3? And it turns out that you can find one of these, and it's actually pretty easy to describe it. So what you should do is you should embed the two-sphere in R3. And in R3, you have the sort of standard, like you have the three standard vector fields pointing in the X, Y, and Z direction. And so what you can do is you can orthogonally project the standard basis at each point onto the tangent space of your two-sphere. So if you have this like point at the North Pole, then like one of those vector fields is going to get projected to 0 at that point. But that's fine because I still have the other two directions that are going to span that tangent space. And then if you kind of look down here at some more generic point, then if I orthogonally project the standard basis vectors to that purple tangent space, I'm going to get 3 non-zero vectors there, and they'll collectively form a frame at that point. And in fact, because the vectors that I originally picked were an orthonormal basis of like R3, and I orthogonally projected them, I actually get that this vector, this frame field that I just cooked up is a parsable frame field. So it came from orthogonally projecting an orthonormal basis, and so it's a sort of rather standard result that that's a way to get parsable frames. So the sort of moral of this story is we weren't able to find a frame field of the size of our vector bundle, but if we allowed it to be a little bit bigger, then we were able to find a frame field, and in particular a parsable frame field. And so the main theorem that I was able to prove with Tom and Clay is the following. So it actually answers all three of those questions from the previous slide. And what we'll see is it answers them in kind of the most satisfactory way possible. So here's the theorem. If you have a rank K vector bundle over a D-dimensional manifold, then you can find a parsable frame of size K whenever K is greater than N plus D. So what is this telling me? All right, so in particular, it's saying that parsable frames always exist for any vector bundle you like. And it's giving you a bound on how big you have to go before you'll be able to find one. Because you could imagine an unfortunate type of situation where you had some theoretical guarantee that frame fields existed, but the dimension was like super large. And so if you actually wanted to find one in practice, like maybe it grew like exponentially in the size of your vector bundle, in which case they wouldn't be a very practical tool because you'd be having to deal with like oodles and oodles of vectors. And so what's happening here is that the size of the frame you have to cook up only grows linearly in the size of the base and the size of the fiber of the vector bundle. So a couple of things to mention is that the previous example shows that this result is not sharp, right? So if you think about the tangent bundle of the two sphere, then D is 2 and K is 2, or sorry, and N is 2. And so this theorem would guarantee a parsable frame of size 4 and bigger on that vector bundle. But as we saw, we could actually find one of size 3. So it's not telling you can't find ones in lower dimensions. It's just guaranteeing that once you get to this sort of critical dimension, that you'll always be able to find them. And I should mention that this generalizes some previous work by Freeman, Poor, Way, and Weiss that sort of talked about some other situations where you're working with parsable frames on vector bundles. So any questions about the statement of the theorem before I talk a little bit about some of the ideas behind its proof? Okay, so the proof of this theorem actually involves some somewhat sophisticated algebraic topology and differential geometry. And I'm not exactly sure. I sort of imagine that a lot of people here's eyes would glaze over if I started going into a ton of the details of that. And so I'm going to try to keep this this very general. So in order to prove this theorem, what you do is you start with your vector bundle, and associated to that, you can build a new bundle that we call the parsable bundle, PK. Or actually, that should be PK of E, not PK of V. And this is not a vector bundle, but it's a bundle where the fiber over every point is the space of all parsable frames of a fixed size K. And so in this context, finding a parsable frame amounts to finding a section of this bundle. So it means you have to be able to sort of continuously make a choice of point in each of the fibers. That's sort of telling you what the parsable frame at each point is. And a while ago, I told you about a geometric characterization of parsable frames. They come from frames whose analysis operator is an isometric embedding. And so if you sort of think about that, what that's telling you is that you can identify the space of parsable frames of size K in an n-dimensional space with orthonormal subsets of r to the k of size n. So basically, you pick an orthonormal basis of your domain space, and you hit that with the analysis operator. And because the analysis operator is an isometric embedding, that's going to give you an orthonormal subset of size k. And the space of all orthonormal subsets of size n in Rk is a sort of well-known geometric object called a Stiefel manifold. And this object has well understood topology. And I won't be very specific about this, but what you can sort of say is that the topology of this space is sort of trivial in low dimensions. So if you sort of look in dimensions less than or equal to the difference in the sizes, then there's sort of no interesting topology there. And then what ends up happening is that there's a sort of well-developed theory from algebraic topology that sort of tells you when you'll be able to find sections of bundles. And what sort of happens is that the sort of obstructions to finding sections of a bundle are given to you by certain cohomology classes on your manifold in dimension up to d. So, I mean, you have these cohomology groups, which are defined in some way, and the obstruction classes are elements of these groups. And if the elements are 0, then you can find sections, and if they're not 0, then you can't. And so the idea is that if k is bigger than d plus n, then because the sort of topology of the sort of fiber space is trivial in all the relevant dimensions, then you sort of see that the obstructions always vanish in the dimensions that you care about. And so you'll always be able to find some sections. So I don't really want to say too much more about this than I already have. But these are kind of the rough ideas of how we were able to prove this. So moving on, I want to sort of talk about some future directions that we've been thinking about. So first, we'd like to kind of develop some algorithms for constructing parsable frames on vector bundles. So we have this theorem that tells us they exist, but it doesn't really tell us how you can construct them. And so we sort of have some ambitions of sort of creating a kind of algorithm that starts with a bunch of random vector fields on your manifold and then kind of deforms them into a parsable frame on that manifold using, like, I don't know, some version of like gradient descent. Another thing we'd like to look at more closely is I sort of alluded to some of the like robustness properties that parsable frames had with respect to various types of noise in the first part of my talk, and we'd like to do similar types of analysis to sort of show what types of robustness properties parsable frame fields will have. So like you could sort of imagine that you have like some noise on your vector bundle that's sort of more noisy at some parts of your manifold and maybe less noisy at other parts. And you might want to know, oh, are parsable bundles still like a very good thing to use there, or is there some other type of frame field that would maybe be better? And then maybe a more theoretical question is this sort of minimal frame dimension. So what our sort of theorem tells us is that once you get above dimension n plus d, you're guaranteed to have parsable frame fields. And unless you're, I mean, and there's no hope of having parsable frame fields in dimension less than n, because they couldn't possibly span. And so the sort of sweet spot is like in the middle of these two numbers. Like, so like what's the sort of smallest dimension in which you'll be able to find a parsable frame for a given vector bundle? And so kind of understanding what that is in various examples is something that we are kind of interested in. And so I'll sort of close that, like, I feel like this sort of technology of vector bundles seems like kind of a useful hammer, and I'm sort of a more pure mathematician, and so I don't know a whole lot about applications. But if you sort of feel like you have any like manifold-based data applications that you think might be useful to apply this to, I'll sort of say that I'm a hammer seeking a nail, and that I'd be very interested if people had things that they thought this might be sort of useful to throw at. And with that, I'll thank you for your attention today.
All right, let's thank our speaker by clicking buttons. I did it. Let's see, did we stop the recording?